Hello, welcome to my chemistry note session. Through these sessions, I will be slowly going through my notes, topic by topic, so for those who may miss, they have something they can refer back to. For those who learn better with recorded lectures, that's something we'll have. But please don't think that means we can just miss our lectures. With this in mind, we'll start with our first session, which is all about definitions and terminology. Ooh, exciting. But as I say in the first slide, gotta start somewhere. So, first topic is chemistry. What is chemistry? Biology is the study of life, while chemistry is the study of matter and energy. The vast majority of the reactions of the subject matter we will study will be inanimate objects and substances that occupy space and the energy flow that occurs within them, between them. Because it's not just enough to say we're studying matter, but what is that matter doing? Now, what is matter? Matter is simply anything that has mass and occupies space. So it contains a weight and also contains a volume. If it does not contain both, it is not matter. Now, mass, this is a little circular logic here, but mass is anything that is the measurement of the quantity of a matter. So how much is present in that given volume? Now, mass is independent of volume because there is a scaling factor of typically the more mass, the more volume an object will take up, but not all objects are the same. Solids, typically heavier objects take up more volume, but you can't relate a pound of bricks to a pound of feathers. They will be totally different volumes. Liquids are also also have matter. Gases, those are a very special type of matter that the mass of that is almost independent of the volume because they can be almost infinitesimally compressed. Even plasma. No, I'm not talking about plasma of the blood, but we're talking about plasmas like high energy, almost like lightning. We're talking about like, if you ever seen Ghostbusters, their zappers that they use to capture the ghosts are essentially ionized plasma. But we don't have to see it for it to be there. Air is the simplest example of that. It's all around us, invisible to the naked eye, but it is there. Now, vacuum, a pure vacuum, not the instrument, but vacuum is the absence of matter. If we were to use a vacuum, to pull a vacuum, to create a vacuum, would be removing all the matter, all the air, all the substance within a box, and only then we have a complete absence of matter. Energy also does not occupy space or have a mass, so it is also not matter. Now, one of the main types of matter we will talk about is the element. It is the simplest type. Each element has a distinct physical and chemical property that distinguishes it from every other element. And we cannot break down an element into something that is chemically simpler and still be stable. So I can have a big chunk of iron, I can have a small chunk of iron, but if I subdivide the iron, it's still iron. Eventually I'll get to a point where I can't subdivide it anymore, and at which point it ceases to be iron. Carbon is going to have a different chemical property. different amount of mass per volume, different amount of different color, different hardness. All these things, there's a point where carbon cannot be broken down anymore. Each element is distinct. When we break down an element to the smallest quantity available, only then have we broken it down into its atomic level. It's the smallest amount of element that is still characterized as an element. Now, how do we hold elements together? Those are going to be through chemical bonds. It's a electrostatic attraction created by the subatomic particles in there that holds these guys within close proximity of each other, these atoms. And when we combine two or more elements together, we form what's known as a compound. Each compound has its own unique set of properties and it has its own unique definite composition. I can have one hydrogen for every one oxygen, and we have H2O2, hydrogen peroxide, an oxidizing agent we use to disinfect wounds. Or I could have two hydrogens for every one oxygen, and that's H2O. That's the water. That's our chemical that is present in the greatest quantity on Earth. Well, one of the ones the greatest quantity on Earth. It's in all over oceans. Now, when we talk about elements and compounds, we can break those down into their own unique subdivisions, where if we have a container containing only one type of element or one type of compound, we can call this a pure substance, meaning that all the particles in that container are of exactly the same kind. If there is any sort of other chemical in there, any sort of other compound that is not chemically bound together, ceases to be pure and it becomes a mixture. Oftentimes, the difference between a mixture and an impurity is a mixture is the quantity of the second compound. Trace amounts of the second compound is often called an impurity, but when it's in significant quantities, even if it's not uniformly mixed, we call these guys mixtures. So, homogeneous. When we talk about a mixture, we can talk about two types of mixtures. The main type is homogeneous. Homogeneous means to be uniform throughout. Homo meaning same. So, same mixture. The idea here is that when you have a homogeneous mixture, the first spoonful is going to be the same as the last spoonful. The simplest type of homogeneous mixture is called a solution. So what we're referring to as solutions. Typically, solutions will be a liquid, and then we have either a solid, liquid, or gas mixed into that liquid. But a solution could be two solids mixed together uniformly, two liquids mixed together, even two gases mixed together uniformly. Air is a uniform mixture of gases. We can have Kool-Aid. We have a lot of different components in there. We have our sugar, we have our food dye, we have our various flavoring components. They're uniformly mixed, so if it's mixed and all dissolved in there, the first sip of Kool-Aid tastes like the last sip of Kool-Aid. And that's how it should be. Now, the opposite would be heterogeneous or heterogeneous. This is an example of a non-uniform mixture. So, hetero meaning different. The idea is that the mixture is not the same all the way through. Sand in water, or a pond, essentially. You can if you start to step into the pond, you stir up all the mud and muck, it gets distributed into the water, but it eventually settles back down. Another such situation would be pulpy orange juice with large amount of pulp. As you shake it up, you redistribute the pulp, but if you don't shake it up before you drink it, you're going to get very little pulp at the top and a lot of pulp near the bottom. Even like things like yogurts and ketchup, that you these things will tend to separate over time. You have to stir them up and mix them up so that they become as close to homogeneous as we can before eating them. You get that little film of liquid at the top of yogurts. That's the separation. So we're mixing them up to reassure homogeneity. Now, we'll often see states of matter as well. We'll see things S stands for solid, L stands for liquid, G stands for gas. But sometimes we'll come across one that's AQ. AQ is a type of solution, it's a type of state of matter to mean dissolved in water. It's a solution in water. AQ stands for aqua. I'm pretty sure it's Latin, but aqua, Latin for water. Now, it comes to properties of matter. We can discuss both the properties of physical and the properties of chemical. We can talk about whether the property and how those properties change. So, a physical property is a property that we can use to identify a compound. It can be observed without changing the compound itself, or at least changing the chemical composition. So the color of a compound can help identify what the compound is. The odor is the smell it gives off, though that means usually the chemicals reaching your nose and being absorbed. The density, that's a real fun one to measure. Density is its mass divided by its volume, and we'll talk more about that in another video. But density can be measured and can be used to readily determine different compounds. Metals, for example, have a very well-known density that will not change. And we can easily, since they will not dissolve in water, we can measure their weight and determine how much water they displace to determine its density. I know it seems like we're changing the compound, but melting point. We can heat a metal or other solid up to its melting point, because even though it melts, goes from solid to liquid, if you cool it down, it goes back to solid again. So it's not truly changed. The same thing with boiling. We can boil thing, and it goes from liquid to gas, but we can also take it back from gas to liquid. Hardness. So the more hardness scale you hit it with a chisel, and you're figuring out at what point does it start to break. Even though I might be breaking elements apart, I'm not changing the elements as I break it. Conductance. How well does it conduct heat? How well does it conduct electricity? I may be running electricity through it, but it's still the same chemical compound. And solubility. Solubility is one of the hardest ones to tell because it does dissolve. It does seem like it's been chemically bound together, but however, there's ways to extract the water back out. So once we've dissolved something, if we can extract the water, it resumes its original shape. Two of which properties that we'll talk about that have their own unique definitions we might need to know. Malleable, capable of being pounded into various shapes. So when we hit a metal, it's malleable, it will bend rather than breaking. You hit a sugar cube with a hammer, it's going to shatter. You hit a piece of steel with a hammer, it's maybe going to dent. smush out, but it's not going to shatter. You hit like a crystal with a hammer, it's going to shatter. But not so much with a with piece of copper. So, and as I said, solubility. Soluble is a term we'll often use. Soluble means able to dissolve or able to go into solution. So, being able to go into aqueous, we say something is soluble. Now, chemical properties are all properties of how does a compound react when exposed to other substances, such as will it burn, its flammability, acidity or basicity, will it react with other acids and bases to neutralize them, and oxidation potential. These are such reactions we will talk about much later. Redox potential of like, will something lose electrons and become a lower charge state, or gain electrons become an upper charge state. Things like vitamin C is a antioxidizing agent, antioxidant, you know. And so we know about that. We know that oxygen, for example, will cause iron to rust. We know about its oxidation potential and iron's oxidation potential. With that in mind, we can also look at and classify these individual properties as being extensive or intensive. Extensive, they are extending as we get bigger. I'm extending this forward. For example, mass or volume. The more you have of something, the larger the extensive property. The intensive properties are independent. So, for example, melting point, the melting point doesn't change just because we have more of a substance. It doesn't necessarily become harder just because we have more of the substance. It doesn't conduct more electricity just because we have more of the substance. So, but solubility, for example, can depend. So there's solubility limits. If we have more of the substance, it may not dissolve nearly as well. So with that in mind, we can also talk about physical and chemical changes. As I said, a physical change is one where the physical appearance may change, but not its chemical composition. This is hard. A lot of the times a physical change can be undone. I can boil water, but I can also condense water. A physical property may change with that because, for example, ice is less dense than water. Ice floats. Steam is way less dense than both ice and water, but it hasn't changed its chemical properties. That it's still H2O. It has not broken any bonds. We can take a big chunk of steel and shear it off. I cannot easily put them back together. It is possible, but it's not very easy. But the fact of the matter is the iron is still iron in both cases. A chemical change is when we rearrange the atoms to form new chemical bonds. These can still be undone with the right amount of energy, but often difficult to do. But the idea is that we're rearranging and making new chemical bonds. So, when I rust iron, I am making new bonds between iron and oxygen. When I burn something as a combustion, I'm making new bonds with oxygen. So, all these examples we can have when we add acid to a base, we're making a new bond between a hydrogen cation and a hydroxide anion, neutralizing to form water. But during a chemical change, a reactant, or oftentimes multiple reactants, will undergo a rearrangement of chemical bonds to become what we call the product. So, largely we've talked about matter and energy. Matter, but not so much about energy. So, there's a few more terminology we need to get in before we are ready to really start. That remember that mass is the measure of matter within an object. This is not the same as weight. We will often use them interchangeably, but is is mass is intrinsic of an object. Weight is the measurement of gravity pulling down on a given mass. And so that means that when we look at mass is always constant no matter where and when it's measured. But weight is directly independent of weight is directly dependent on where it's measured. My weight in on the moon is going to be much less. My weight on Jupiter will be much more, though the same amount of mass remains, because the gravity will have changed. Now, when we talk about energy, energy is the capacity to do work. Work has to do with a force being applied over a distance. You can imagine someone rolling a giant boulder up a slope. So the force it takes to push it up the slope times the distance that boulder is going to take. Now, one of the key features of this is that the law of conservation of energy, that energy can neither be created nor destroyed. All that means is that energy is going to be transferred from one object to another. We're going to have energy stored within bonds. We're going to break those bonds and form new bonds, and in that process, energy is going to be transferred from here to there. Now we're going to try to extract some of that energy. Oftentimes, you try to run a car, you're taking the energy you're getting from the combustion of your fuel and using that to turn your motor. But the amount of energy we can get is maximized by the amount of fuel we burn. We cannot get more than the amount of energy created in there. No matter what we're doing, energy is only being converted from one thing to another. Now, there's a lot of different types of energy, many of which we will not deal with. Heat energy, that's a big one we will deal with. Energy can be transfer of can do work via heat. There's chemical energy, often seen as the bonds. Mechanical energy, which is the purview of physics, are kinetic and potential energy. Electrical energy, which we may talk about later, but it largely has to do with electrons being transferred. It's the thing that runs our circuits. Nuclear energy, energy that comes when atoms decay, break down. Sound waves can be a type of energy. And another type of energy we'll talk about is electromagnetic, which is light. Type of energy that can be transferred from one place to another. Now, one of the last slides we'll talk about is the scientific method. So, the scientific method is the basic scientific process that combines observation, hypothesis, and experimentation. This is how we approach nature. If we haven't used the scientific method, we're not doing a good job. The idea is that whenever you get an idea, it stems from an observation. You see something happen, and then you make an educated guess on why that may happen. An educated guess that can be tested. This educated guess is our hypothesis. It's a proposed explanation for a body of observed facts. You observe this occurs. Why does this occur? You're going to make a reasonable guess, and it should be testable. we want to say, why does this work? Well, you run an experiment, and so you have two possibilities. I mean, there's shades of gray, but either the evidence supports the hypothesis or the results are inconsistent with the hypothesis. More often than not, the results are inconsistent, whether it's even partially right or all wrong. We need to revise our hypothesis to match what we have. So we revise our hypothesis to knowing that this wasn't spot on, and then we rerun more experiments and see what we can do. If the evidence does support the hypothesis, you're going to want to present that data. You're going to want to run more experiments and make sure that you're indeed right. Once you have enough data and you can publish that this is what I think is happening, you often give other scientists a chance to test and see whether you've overlooked a glaring error or not. So with that in mind, you need to be able to figure out this needs to be testable by other scientists. If they can't get the same results, maybe you faked something, maybe you made some error that you did not account for. There's lots of different reasons. Not every experiment will necessarily be tested by others, but a lot of the good ones will be. Only then, if enough experiments are successfully produced, you develop a scientific theory. Now, a theory is a hypothesis that will not only explain the data correctly, but it should also withstand repeated tests and generally is widely accepted among the scientific community. So it's not just like it's not just like, well, one guy thinks it's right. It's the 9 out of 10 dentists agree that this toothpaste prevents tooth decay. It's the 9 out of 10 scientists believe this is the correct explanation. That usually a theory is much broader in scope than a simple hypothesis. It can explain and predict many different observations that are linked to the same underlying phenomena. Like, you can explain all the little facts about what happens when lightning strikes. Why does lightning strike metal more often? You say, why does it create thunder and all these such things? And like, why does your hair stand on end before lightning strike? Why is it striking taller objects? You can know all these things. If you have a correct theory, these should be able to be explained. Now, while the hypotheses are usually undergoing continuous revision, the resulting theory is supported by all the prior experimentation and all the evidence. It's not very good. It's not going to be a theory if there's a glaring flaw that is not being explained. Typically, a theory has undergone the most amount of scrutiny and thus are the most reliable. Now, this is completely independent of what's called a scientific law. A law is simply a statement of consistent behavior of a natural phenomenon. That the theory is an explanation, the law is just a statement of fact. A statement of fact that always occurs under a standard set of conditions. It's saying if I drop two objects from the top of a tall tower, regardless of their mass, as long as we can neglect the air friction, they will hit the ground at the exact same moment. If I drop two objects in a pure vacuum, whether it be a bowling ball or a feather, they will hit the ground at the same time because they're both experiencing gravity. So, scientific law doesn't explain why this occurs. It's just a statement, like the law of conservation of energy. It doesn't explain why energy can neither be created nor destroyed, just that energy cannot be created or destroyed. So here's some little facts. A hypothesis is not an educated guess. It's rather a tentative explanation for facts based on reason and evidence. It's so that a theory isn't just a hunch or an explanation made out of thin air. That may be the colloquial idea of a theory, but a theory, the theory, when you talk about like Sherlock Holmes, it's an idea based on a few facts. But in science, a theory is an explanation that has never been contradicted by evidence. Even that does not prove a theory correct. All this proves is that it has yet to find the evidence to refute it. A theory is kind of like an X-ray. An X-ray is actually a negative image. When we shoot X-rays at a photographic film, the negative image darkens. Why we see the white bone is where all the X-rays got absorbed by the dense bone. Now, a theory is similar, that all other possibilities are disproven, but the explanation fits for the given fact. Take the cartoon image to right. Can you tell what character that is based on the hole created in that wall? Most of us probably could. Does that mean that is guaranteed to be that character? No. However, is that going to be Porky Pig? Probably not. That wouldn't fit. Would that be Elmer Fudd? Probably not. Yosemite Sam? Probably not. Yosemite Sam's a little shorter and would have a big funny hat. But the fact of the matter is, we cannot be absolutely certain. However, the facts suggest that it is a creature with a long, bushy tail, a creature with long, pointy ears. Now, the bushy tail would suggest it's not Bugs Bunny, but the pointy ears would suggest it's something that has long ears like Bugs Bunny. So, who could it be? Most of us will know. A law is not simply a correct theory. A law is the observation. Theory often explains the law, but there is no way to convert a law to a theory or a theory to a law. Another example of a law of conservation of mass. In any chemical or physical change, the total mass present before the change is equal to the total mass present after the change, if you're collecting everything. If I take a log and I burn this in a sealed chamber, the mass of the chamber before and after the combustion is the same. If I'm collecting all the gases, the ash makes up a small portion. The gases produced will make up the major portion. That's simply put. If I put 5 grams of this with 5 grams of that, my total mass of solution should be 10 grams, even if the atoms have rearranged. This law, this statement, allows us to do a lot of our math that we know we cannot suddenly gain or lose mass. It's simply atoms are rearranging. So that is as far as we're going to get when it comes to our basics of our definitions. Thank you for your attention.